Welcome to the Explainer. Today, we're diving into a question that every single person in machine learning has to ask themselves. You've just built a model, but how good is it really? How do you know how it's actually going to perform out there in the wild? Let's get into it.
It just makes sense, right? The more training data we give a model, the better it should get. And that whole idea is captured by something we call a learning curve. So here's what a typical learning curve looks like. As you pile on more training data, the performance gets better and better, but only up to a point. Eventually, it just hits a ceiling and levels off. It saturates. The million-dollar question is, how do we accurately measure the performance at any given spot on this curve?
Okay, so to measure that performance, we've got two main tools in our toolkit, the good old holdout method and something called cross-validation. The holdout method is super straightforward. You just take your data and split it once. You get a training set and a test set. Boom, done. Cross-validation, on the other hand, is a bit more involved. Instead of one split, you split the data multiple times. You train and test on each of those different splits, and then you average out all the results.
So, we've got our tools, but are they any good? I mean, how reliable are they? Ideally, what we want is that as we get more and more data, like an infinite amount of data, our performance estimates should get closer and closer to the real, true value. This idea, this desirable property, has a name in statistics. It's called consistency.
Okay, now don't let this formal definition scare you. I know it looks like a bunch of math jargon, but the actual idea behind it is incredibly simple. Let's just break it down.
That's really all it is. A consistent estimator is simply one that gets more and more accurate the more data you throw at it, which, is exactly what you'd hope for from a reliable measurement tool, right?
And this, my friends, leads us to the big twist in our story today. Are the holdout method and cross-validation actually consistent? The answer? Well, it just might surprise you. All right, get this. The holdout method is generally not consistent. And you might be asking, why not? Well, think about it. It's based on just one single random split of the data. You could have gotten lucky with that split, or you could have gotten super unlucky. Cross-validation, however, is a different story. It is mostly consistent. By averaging the results from all those different splits, it kind of smooths out the randomness and gives you a much more stable picture of the algorithm's true performance.
Okay, so it sounds like cross-validation is the clear winner. Case closed, right? Well, not so fast. In practice, the best tool to use depends entirely on the specific question you're actually trying to answer. You see, there are two main ways to look at this. First is what's called the conditional view. This is when you're asking, how good is this one specific model that I just spent all this time training on this specific data? Then there's the unconditional view. This is a much bigger picture question. It's asking, how good is my learning algorithm in general, on average, across all the different training sets it could ever possibly see? So let's bring it all together and connect this back to our tools. Choosing the right one really just comes down to matching it with the right question.
And here it is, the final verdict, laid out nice and simple. If you are asking that conditional question, how good is my one specific model, you should use the holdout method. It gives you a direct, unbiased estimate for that single model. But if you're asking the unconditional question, how good is my algorithm in general, then cross-validation is absolutely your friend. It's all about reducing the randomness from a single split to give you a much more stable and reliable answer.
Now, there's one last little catch with cross-validation you got to keep in mind. Remember that learning curve? Performance gets better with more data? Well, in cross-validation, each fold is trained on a subset of your data, so it's a little bit smaller than your final model's training set. This means the performance estimate you get from CV can be a little pessimistic, a slight underestimate of how well your final fully trained model is actually going to do.
So what's the ultimate takeaway here? Estimating a model's true performance is surprisingly complex. In fact, it's been mathematically proven that there's no such thing as a perfect, unbiased estimator for the variance of cross-validation. It's just not possible. And that's a powerful reminder that in machine learning, even with our best tools, there are always going to be fundamental limits to what we can truly know for certain.